Good evening. In this video, we are going to talk about proposition 47 from book 1. It is also very well known as Pythagorean theorem. Okay, so this proposition declares that if we are given a right angle triangle here, then the square on the side subtending this right angle will be equal to the sum of those two square angles on the sides that containing this right angle. Okay, so first of all, please recall definition 21. What is this right angled triangle? So it is a triangle contains a right angle. Okay, so let's assume angle C is a right angle here, and let us apply proposition 46 we've just proved to construct three squares on three sides of this triangle. So they will be three squares. Great. And let's mark them as D, E, F, G, H, I. And for convenience, let's give them some simple names as square 1, square 2, and square 3. So the proposition declares that square 1 plus square 2 will be equal to square 3. Okay? Let's give it a proof. So please think about proposition 31. We are able to construct a straight line that is parallel to a given straight line through a point not on it. So let us construct this straight line through point C that is parallel to AD. Okay? And let's assume it meets these two straight lines at point of J and K. Okay. So in the next step, let us use postulate 1 to join BI and CD together. Okay, as well as CE and AF. Okay, so in the next step, let's prove HCB are in the same straight line as well as ACG. Okay, so we know that angle ACB is equal to right angle, and angle ACH is also a right angle because of definition 22 of a square. It is right angled. Okay, so this is the interior angle of a square. They are right angles, and if we apply if we apply common notion 2 and add them together, we know that angle ACB plus angle ACH will be equal to two right angles, right? And let's think about proposition 14. If two straight lines are falling on a point of a straight line and they are not in the same side, and if the adjacent angles, the sum of them are two right angles, and then these two straight lines are in the same line. So for example, we have the straight line AC and point C, and HC and CB are absolutely falling on different sides of AC, and the adjacent angles here, ACB plus ACH, are two right angles, which means HC and CB are in the same straight line. So let's write it HCB are belonging to the same straight line. So with similar proof, we can conclude that ACG are also in the same straight line. Okay, that's great. And please think about this square, ACHI. We know from the definition, we know that AC will be equal to AI, correct? And in the big square S3, we know that AD will be equal to AB, correct? And also because of the definition of square, we know this angle is right angle, and this angle is also right angle, correct? And if we apply postulate 4, we know that it is postulated that all right angles are equal. So this is right angle, this is right angle, so we know angle IAC will be equal to angle DAB because of postulate 4, right? And if we apply combination 2 again to add the same thing to both sides, we know that angle IAC plus angle CAB here, sorry, it's B, will be equal to angle DAB plus angle CAB. And what are the left side? It is angle IAB, and the right side will be angle CAD, correct? And if we put this condition here, angle IAB equals to angle CAD, and combine them together, and we find that in terms of these two triangles IAB and CAD, they have the relationship as equal sides, this and this, and equal angle, this and this, and another pair of equal sides, AD and AB. So if we apply proposition 4, we know that side angle side, we know that these two triangles are equal. ABI equals to triangle ADC, correct? That's great. And let's have a look at this parallelogram. Okay, we know that AD is parallel to CK, correct? And AJ is absolutely parallel to DK. So ADKJ is a parallelogram, right? And if we apply proposition 41, we know that if a parallelogram and a triangle have the same base and they are in same parallels, then the parallelogram will double the triangle, correct? So which means let me check, DKJA, this, okay, it will be equal to twice as triangle ADC, correct? And similarly, in these parallels, if we apply proposition 41 again, we know that AI is parallel to BH. Please pay attention to BH here. We have proved BCH are in the same straight line, so we can write it that. Or otherwise, we only know that AI is parallel to CH, but we don't know AI is parallel to BC, okay? So it means that parallelogram, or let's say, simply say it is square. So square 1 is equal to double of the triangle, this AIB, correct? AIB, right? And if we combine these two equalities together, we can simply imply that square 1 is equal to parallelogram DKJA, correct? DKJA, this parallelogram, or let's say this rectangle, is equal to this this square. And with the exactly same method, we can prove that I'll skip the steps, okay? We can prove that square 2 will be equal to parallelogram BJKE. Oh, sorry, is this side. BJKE. Correct? And if we add these two equalities together by applying combination 2, we know that S1 plus S2 will be equal to parallelogram DKJA plus parallelogram BJKE. So what is this? We add this parallelogram to this parallelogram, and the result is absolutely the square S3, correct? So we have proved the sum of these two squares is equal to this square on the side subtending to the right angle, which concludes our proof. Great. So in the next video we are going to talk about proposition 48, and thanks for watching. Have a good day.